Hey, Chris, I've been hearing a lot about vLLM. Students been asking about it. Like, is it really that much better than everything else out there for inference and serving?
I mean, it's pretty good. Yeah.
What makes it so good exactly? I mean, it's got kind of a confusing name.
Yeah, there's a lot going on under the hood here. So there's a lot of novel optimizations that they made with things like PagedAttention, better handling of GPU memory blocks, using things like graphs to help inference optimization, quantization, and more. They're basically, they threw the kitchen sink of optimization at it.
Man, that sounds like a lot. Uh, you think we're going to be able to give everybody some deep intuition and cover this thing today?
That's the plan, Greg.
I think we are too, man. All right, we're going to see you back in a while after we dig into the first principles of what's kind of going on here to show us exactly how to set up that efficient inference and serving. See you in a bit, Chris. I'm Greg. That's Chris. We're co-founders of AI Makerspace. And today we're going to talk vLLM. We're going to discuss exactly what we mean when we say words like inference and serving. We're going to try to understand how vLLM reduces memory bottlenecks created as words flow through transformer architectures. And there's going to be a lot today. There's going to be a lot. We're going to use some key analogies to try to help you guys kind of understand this deeply. And we're going to do our very best to build this up one simple idea at a time. We'll be collecting questions along the way, so check those out in the YouTube chat. Drop them in Slido if you got them. But for now, let's go ahead and kick this thing off. Efficient LLM inference and serving with vLLM. As always at AI Makerspace, we want to align our aim. And I want to just review the ideas of inference and serving first. Then we want to understand really what's happening at sort of a architecture and a data flowing through the transformer level so that we can understand where these memory bottlenecks occur. And then, of course, Chris is going to show us how to actually use vLLM. The thing that's great about using it is that it's super easy to use and it's fast. So we'll kind of cover inference and serving, then we'll talk vLLM, and we'll sort of take a number of tangents and asides to get to the point of what a K&V cache is and why we would need it. And then we'll talk a little bit about the PagedAttention algorithm that is really intelligently leveraging that K&V cache before we build. Okay, let's talk about the most simple things that we need to start building this idea up in our head with. The first is inference. And if we just like look up the word inference, it means a conclusion reached on the basis of evidence and reasoning. Okay, so the example, like top example from Google, is researchers are entrusted with drawing inferences from data. This is useful because what we're saying when we do inference or when we perform inference on a large language model is that we're saying we're making predictions, we're generating outputs, we're taking our new data that we haven't trained the model on, we're running it through, and we're, as a result, drawing inference from that data. And I found this this quote from Cassie online: "Statistics does not give you the truth," and this is her meme here. And I don't think this idea of inference needs to be so complicated, although for whatever reason people sort of like to use it in complicated ways. We say things like at inference or at time of inference or at inference time. But, at the end of the day, what we're talking about is like flowing through the network. However complicated the network is, we're just taking the new data, we're flowing it through the network, we're predicting something out. This is the simple, super simple example here. Of course, with LLMs, we're doing this in larger transformer architectures and all of that. But doing inference is not something that's ridiculously crazy. Okay. Now, doing inference can be done locally. This gets us into this idea of serving. When we build large language models, when we build machine learning models in general, we've got to first deal with the data, extract, analyze, prepare, transfer, load, ETL, whatever. We got to deal with the model, train it, evaluate it, validate it, make sure that it's good to go. We might also do some alignment, some fine tuning with LLMs. Once we have everything ready, we can do inference. Then we're ready to serve this thing up. Because serving it up is simply making it available to other people, making it available for others. Now, a simpler way that many think about serving is it's deploying to production. But is that simpler? Well, in a sense it is, because you can just say, to serve is to deploy, done, full stop. Meaning that if I'm on my phone here and I want to request something out of an application, that application is going to go then make a request to a service. It's going to then get a response back from that request. If the service is a machine learning or an LLM model as a service, let's say, then I'm going to get the output of that LLM back, and then I'll serve that thing up directly back to the user. So ChatGPT on your phone, right, is kind of doing this type of thing. But, there's this sort of serve language that's very confusing sometimes. And really, when we talk about serving and we use analogies like this guy who is looking like he's a server, it gets a little bit even more confusing. He's serving up this AI on a platter here. And maybe that's not the best way of talking about this, because it's kind of conflating a couple of things. When we talk about serving up a model, the model is actually served from back in this service. What's happening at this web app, what's happening at this web application interface is we're actually just interfacing between the client and the server. Now, of course, many of you know this, but this idea of the interface is simply the API. It's the application programming interface. So the servers, the wait staff, really are more like APIs. They kind of connect the people out in the restaurant to folks in the kitchen. They're the go-betweens. They're the messengers. They take the request from point A, they go to point B, and then they return back with some information, or in this case, some delicious food to point A. So the restaurant analogy here is that the customer is going to make a request to the API. The API is going to push this to the server. The response is going to come back through the API and be delivered to the client. Now, the food made in the kitchen is the same food that's made that the customer gets delivered on the plate. So I want to introduce some terminology here that's going to come in handy for us to understand vLLM. I want to sort of introduce this idea of query, key, and value. one thing we might say is we might say that we could use this language is that the customer might come in and they might say, you know, well, I'm kind of just in the mood for something a little spicy. Maybe it has a little sweetness to it, something with maybe some chicken, you know, kind of a little, some fresh vegetables on the side. And maybe I'm giving some information to the waiter that the waiter has to then kind of absorb, kind of say, okay, I understand. I'm paying attention to what you're saying with your request. And knowing what I know about what's on the menu, I'm going to try to find something that's similar to what you're asking for. So I'm going to sort of key in on something that seems very relevant to your query. And I'm going to help you select that because it sounds very similar to what you asked for. So in this case, the customer has a query. The waiter is kind of helping them pattern match that query to something that's on the menu. And then the real value is coming when we not only provide the request to the kitchen makes the dish, but when we actually return the cooked dish to the customer, right? You ask for something, that's the query, you get the value at the end. All right, put a pin in this. We'll come back. Now, to summarize inference and serving, you serve a model to allow it to do inference or perform inference for others. All right, easy. Now, let's talk about vLLM. It's easy, fast, and cheap LLM serving for everyone. All right. Makes sense, right? Now, one of the cool things about the backstory of vLLM is that it was funded out of an open source AI grant. This was the open source AI grant program from Andreessen Horowitz, also known as A16Z. So super cool that they got funded by one of the premier VCs ever to do this open source AI thing. And the original page that was posted, September 6th last year, they said this is a library for high throughput LLM inference. Okay, so turns out now these days it's actually inference and serving. So what we'll see later is we'll see how we can do offline batched inference very, very well with this, which is pretty cool. And you can do it very, very simply. So this is sort of the inference aspect. And you can also do online serving. And this is going to be a FastAPI based setup. Chris will go into this a little bit more in a while, but this is also very, very, very easy. And of course, the vLLM inference engine integrates with other serving libraries as well, in case you're particularly partial to them. And sort of the high level that we need to sort of try to understand is that this high throughput aspect, easy, fast, cheap, high throughput. So this is the main plot from the vLLM blog. And you see throughput is on the y-axis here. Throughput is requests per minute. Remember we were talking about requests and responses. So these requests are being made. This is when each request asks for one output completion. And what we see is we see like this big number. Their big numby here is the 24x higher throughput than Hugging Face Transformers, HF, and Hugging Face Text Generation Interface, which was sort of the state of the art text generation inference, not interface, which was sort of the state of the art in kind of achieving high throughput for LLMs. prior to this VLM being released. And you see we're doing sort of Llama 13 billion, Llama 7 billion. We're doing on a couple different GPUs. But, blue bar is higher. And down here we see also for parallel output completions. Okay, we're going to eventually get back to parallel output completions, but it's going to take us a little while because there's a lot that goes into this. Each request asks for one output completion. So the question we need to answer today is, well, how does this work exactly? And the answer, if you just read the blog, it's like, oh, it's so easy. It's page detention. Look at this very simple GIF, and it's clear, right? The performance of LLM serving is bottlenecked by memory. Page detention is clearly the solution. Look at it. There's a great GIF. It's so clear. But there's actually a lot going on here. And if you're not intimately familiar with every aspect of how attention is calculated, then it's kind of hard to understand what paged attention is. And I've highlighted here query, key, and value vectors. So we need to sort of take our first aside here, and we need to go back to some basics of LLMs, ones that are actually used today. The ones used today mostly are decoder-only style or GPT style models. These are auto-regressive, quote, auto-regressive. This is the predict the next word based on previous words. And obviously that's very good for generating the next word for generative tasks. And this sort of idea of this auto-regressive decoder is just use the output, append it to our input over and over and over and over. Start of sequence, A. Take A, append it to our input. Then we get B, and so on, right? This is the auto-regressive decoding. Now, if we back up even just a little bit further to try to understand exactly what's going on inside of this decoder only, we're going to need to understand what's coming into it. So we've got our embedding, we've got our positional encoding, and it goes into attention. So a couple of things we want to keep in mind as we have this discussion, because we eventually need to talk about the K&V cache. When we tokenize, we're chopping words up. Generally, these are subwords in practice, but we're going to sort of deal with full words today because it's going to make it clearer for us intuitively. And then we have embeddings, which is taking those words, turning them into numbers. Finally, we add some positional encoding. So we can not just have the embeddings stacked on top of each other and sequenced, but we can actually connect exactly how they're sequenced through this positional encoding. And so, eventually you get this sort of representation that combines embeddings and positional encoding. And you can kind of shove this into a decoder, an LLM. And you can do this to get that auto-regressive, use the output and append it to our input over and over vibe. So, this is from the Illustrated Transformer by Jay Alamar. If you ignore the left-hand side here and focus in on the decoder side, you see K and V. Look at this. They're coming in. We also see that we've got this sort of embedding and then this sort of encoded embedding going into the decoder. Finally, we get our outputs at each decoding time step. And if we zoom in on the decoder, we actually see that we need this self-attention to be calculated first. So This K and V that are for the encoder decoder, they're going to go kind of into this encoder decoder attention. We don't really need to pay attention to that for today's purposes. Let's instead try to focus on how we would move from our representation going into the decoder, therefore into the self-attention layer, and how that's going to manifest itself in an attention calculation that has its own Q, K, and V. All right, so self-attention, just at a high level, it's looking at each token and it's trying to decide which other tokens are the most important to kind of understand its meaning. This is sort of attention in general. This is sort of outside of the actively auto-regressively decoding thing that we've already kind of discussed. And attention from a calculation perspective is happening in this scaled dot product attention form. As you add multiple heads to attention, and again, we focus on this decoder only stack, we start to then have a little bit more complexity associated with our calculation, but we really don't need to focus too much on this or on this to understand the K&V cache. We really want to kind of understand this a little bit better. Now, from the original attention is all you need paper, attention is defined like this. An attention function can be described as mapping a query and set of key value pairs to an output. Okay, cool. The output is computed as a weighted sum of the values. Okay, starting to get a little gray here, where the weight assigned to each value is computed by a compatibility function of the query with the corresponding key. This compatibility function, QK transpose, in this equation from the paper. Okay. Now, this compatibility function is important, and it's got interesting analogies to things that we've already talked about before, if you're an AI Makerspace follower. But just very, very simply, first, query, key, and value. Let's consider that the query is the new token. The token that we're looking at now. We're going to try to decide how much the other tokens around it are related to it. And we're going to do that by leveraging this attention calculation. The key, K, is going to be every token in the sequence up to the token that we're looking at. Because of course, we always want to be predicting the next token. We can only look at what's happened previously. The value is also going to be every token in the sequence up to our new token. Okay, I know this might start to feel like it's getting a little bit confusing, but note that K and V, K actually goes in with Q, V does not. All right. We're kind of down the rabbit hole, but I'm going to take another aside here, and I will pull this all back together. I'm going to take a hard left into RAG, okay? Today, it's one of the most important applications out there, Retrieval-Augmented Generation. Now, if you watch our stuff, you're probably super familiar with this already. If you don't, the super high level is this. Retrieval is all about finding references in your documents. Augmentation of the prompt is all about adding references to the prompt before it goes into an LLM. And if you do retrieval right and you add it to the prompt, you can improve your answers and you can ground them in your own documents. You can make them fact checkable and you can basically get better outputs. So there are three easy pieces to retrieval. One is you ask a question. you provide a query, right? Then you search a database for stuff that's similar to the question, and then you return the stuff. Now, how does this work exactly? Well, it works by you have a query, you run it through an embedding model. Embedding model is all about taking the text, turning it into numbers, a vector. Then what we do is we look within our vector database, which is all of our documents turned into numbers, and we look for similar stuff to our query. Cosine similarity is the calculation that's done here. When we find that similar stuff, we go ahead and set up a prompt template to allow us to shove that similar stuff into an LLM, a chat model. And we prompt it with a system level instruction, something like use the provided context to answer the user's query. And then, don't lie to me, say, I don't know if you don't know, et cetera, et cetera. But the point here is that we take the stuff we found similar to our query, we shove it in, and we improve our answer, rather than simply just going and asking the chat model in the first place. So in this case, and none of these analogies are perfect, but in this case, you might say the query is the question that we asked. Of course it is, that's our query. The keys are the sort of documents in our vector database that we're comparing to the query. Okay? Cosine similarity. The value, we might say, is all the documents in our database scored for similarity to the query. All right. Cosine similarity, right? Cosine similarity. Why does that matter? Well, if you harken back to, linear algebra, cosine similarity is calculated with a dot product. And of course, a dot product is basically the same as multiplying one vector times a transpose vector to get a single scalar output one by one. And it's a dot product, right? Cosine similarity is a dot product. Why does that matter? Well, because attention is also a dot product. So when we have our query of our new token, we have our key, which is every token in the sequence, our value, which is also every token in the sequence. Not entirely dissimilar to our RAG analogy, where the key was sort of the docs in the vector database to be scored for similarity. V is the documents scored for similarity. We can kind of remind ourselves as well that attention is all about this compatibility function. Compatibility, Q times K transpose. We're sort of deciding how compatible is this new token to all other tokens in the sequence, right? How compatible is our query to all the other tokens in the sequence? Let's look at a very simple example. Now, even if there's nothing in the sequence yet, there's always some token that exists within K and V. So consider a first pass example where K and V are start of sequence tokens only. They don't have any actual words associated with their token, but they're just start of sequence tokens. And then we have a query, which is our new token, and it's I. Okay. What we're doing is we're saying, okay, I'm going to take I. I'm going to look and see how compatible it is with stuff in K. And I'm going to try to predict the next word based on that compatibility. I'm going to, based on that similarity. It's a loose term, right? And maybe the output of the next word is have. Okay, let's stick with this example. Second pass. Now I'm going to go and I'm going to say, okay, now my query is the output from the previous pass, have. And now my key and value is going to be start of sequence I. Start of sequence I. And in the first pass, this should be start of sequence I. Start of sequence I. That's a that's a slide error, because K and V are going to be every token in the sequence. Okay, start of sequence I, start of sequence I. Second pass is going to be start of sequence I have, start of sequence I have. Output is going to be no. Okay. Third pass is going to be new token, looking at no. Start of sequence I have no. Start of sequence I have no. Next word is going to be interest. Okay, why is this important? Well, it's important because, as you'll notice, as K and V grow, most of what's happening in K and V does not change. In fact, start of sequence I have, start of sequence I. As this grows, more and more of it does not change with each iteration, with each prediction. So it starts to beg the question of, if these are already available in exactly the form we need them in, how can we be more efficient when it comes to running new tokens through our attention calculation and thus through our decoder-only GPT-style transformers, right? Because it's not that every time we're in the restaurant and there's a specific request on the menu that we need to go look at the menu again as the waiter. We already know what's on the menu. We sort of held it in memory in the right place, and we fetch it and retrieve it when we need it. We know what the cooked dishes are. And this is why we need to cache these keys and values, because they don't change except for that new token. And this is the magic behind vLLM, is the KV cache. Now, it's more than just the KV cache. It's PagedAttention, because PagedAttention doesn't just cache K and V. It partitions the KV cache in a special way. And so it intelligently caches K and V. By intelligently caching K and V, what we can do is we can massively increase throughput. So, from the blog, like, these blocks are allocated on demand as new tokens are generated. Well, of course they are, right? So memory waste doesn't happen outside of that last block of a sequence. And so this is sort of like approaching this sort of near optimal memory usage, which is very, very cool. Boosting efficiency, It allows us to batch more sequences together, increase GPU utilization, all the stuff that Chris was sort of mentioning at the beginning, it allows us to do, which is very, very cool. And also, in addition to that, what PagedAttention allows us to do is it allows us to efficiently share memory for parallel sampling. Remember this sort of second diagram we saw? So multiple output sequence generated from the same prompt is also easier when we intelligently cache K and V. And this is, of course, what we're seeing down here, 3 parallel output completions. All right. So this is what you need to know to understand exactly kind of what's going on behind the scenes. I encourage everybody to dig in a little bit deeper to exactly what's happening in PagedAttention. But what we're going to show you for the rest of the session today is we're going to show you today's, well, it's not really a build. Because again, like, what are we doing? We're just like doing inference, right? So what we're going to do is we're going to show you that if we look at one of the models that they have support for, one of the new latest and greatest, right? Mistol, we're going to go ahead and pick that one up. And we're going to show you how to efficiently do inference, batch inference offline, and we're going to show you efficiently how to serve it up online. So our model for the day is going to be Mistol 7B v0.1, and that's all we need to hand it over to Chris, the LLM wizard, to show us how to do efficient inference and serving with vLLM. Chris, over to you, man.
Hey, thanks, Greg. Yes. Okay. So that was a lot to digest and take in. However, luckily for us, the implementation of this is largely trivialized by how good the vLLM library is. So we're going to talk a little bit about what's happening under the hood here, but for the most part, we're just going to walk through how we can actually leverage this. So first thing we'll need to do, of course, is grab our vLLM dependency. We're going to first take a look at the offline batched inference. And that is as simple as follows, right? We're going to go ahead and we're going to import the LLM class and the sampling parameters class from vLLM. We're going to set up a list of prompts that we wish to run batched inference on. We're going to set some sampling parameters here. So sampling is referring to when we're actually decoding our output, right? We're going to wind up in a situation where we put, some number of tokens down, right? We have to choose which tokens to put down. And because we're choosing which tokens to put down, we have a number of different methods we can use to do that. In this case, we're going to use a sampling method, which we have a, mid temperature. So we're going to, have some creativity, as it were, from our model. Our top P of top 95. And then our max tokens, this is just set for an example of 120. So this is how, when we're doing that offline batched inference, we have the ability to set different parameters that relate to generation. And again, because this method works with a number of different decoding methods, we can set a ton of different parameters here. Now, when it comes to the LLM, all we have to do is point this to a model that exists on Hugging Face and is compatible with the vLLM library. Now, very importantly, the vLLM library is not compatible with every single model. So when we look at the actual integrations that we have available to us, it's not every one of them. So what we'll do is we'll take a look at their GitHub repo, and we can see here that we have a fantastic repo, and then we have a number of models that vLLM is compatible with. It is possible to submit a PR to the vLLM library to add new models, and most models work off their base and then derivative versions. So the idea here is that it's not just DeciLM, for instance, it's also DeciLM 7B Instruct. It's the same thing with our Falcon series of models. But the idea is that it's not just the kind of base model, but also the derivatives that have the same architecture. So you can see here that our Llama and Llama 2 models include, Vicuna, Koala, OpenLlama, and more. So this is very powerful, but it does mean that VLLM is limited to a certain subset of models. Now, if you were to say fine tune or continued pre-train a model that's compatible, that would continue to be compatible. So you don't have to worry about, if you fine tune a model, it's no longer compatible. Unless you change the architecture, you're gonna be fine. So all we have to do is point at this compatible model on Hugging Face, and it's going to download that model. It's going to load it into our GPU memory, and then it's going to create some CUDA graphs. These CUDA graphs are a way for us to improve the efficiency of our inference. So we're going to use these optimized constructed graphs in order to accelerate our inference, which is going to reduce inference latency. So we'll be able to generate more tokens per unit time, which is huge, right? Excuse me, sorry. The idea is very straightforward. One second. Very sorry, there's a cold going through my house. Please excuse me. The idea is straightforward, right? We have the ability to load these into memory, and then we have the ability to improve their efficiency by doing a number of pre-processing steps, which includes this graph conversion. Now, I'm just going to show you this. In order to do that offline batched inference, which is 3 prompts at 120 tokens, we're able to do all of that on a single A100 using no more than 32 gigabytes of memory in 1.69 seconds, right? So we generate all of this text in 1.69 seconds, and that is it, right? So this is why VLLM is so powerful. If you were to look at an example of this from previous notebooks, you are going to see that the inference time for even one prompt is about 1.69 seconds using, say, Hugging Face's Transformers pipeline. So really keep in mind that this VLLM is a massive improvement over kind of just using a pipeline. And that's all we have to do. We load the model, we set some sampling parameters, and then we have it, generate over those prompts. And that's it. Now, when it comes to the server part or the server, the model serving, it's a little bit different, but it's still very straightforward. This big block of code just exists to clear our GPU cache. So because we do have to load everything into the GPU, in order to unload it, we need to take some specific steps, and these are provided for you in the notebook. And then we're going to look at how we actually use this VLLM tool in a, say, production or server environment. So what we can do is first take a peek at our terminal. In our terminal, we are going to run a very specific command, which we'll look at in a second. And that's all we do. All we do with this is basically call it as if it were an OpenAI endpoint. So all you have to do is run the command to get this thing up and running, which is just this Python -m VLLM entry points OpenAI API server with the host, with the port, and with the model you want. And that's going to spin up a FastAPI server that you can then ping with requests using curl or whatever your favorite tool to ping is. And then, of course, integrate into an actual API, that your users are using. But the idea is that's all you have to do. And when you do that, you are ready to rock. We are now able to manage requests from our server. And that's it, right? This was the entire barrier to entry. Absolutely huge. And you can see here we've made some requests. So we can send a request with Vancian Magic is, and then we can give this thing a run. And we can see that very quickly we get a response that's, in this case, up to 100 tokens long. And that was real time. That's not saved or cached. That is really how long it took to get that full 100 token response, right? So it's very quick. and it's very easy to set up and use. Now, how does it actually work behind the scenes? Well, first, of course, it's using FastAPI to manage requests coming in from users. And then under the hood, it does a couple very important things. First off, it spins up a number of workers. That number of workers is dependent on the memory capacity you have. It can use, it can use the parallelized options for GPUs, so it can be across many GPUs or distributed. So you can use, if you have, say, a cluster of GPUs, you can use all of those in concert with vLLM. Once it has a number of workers, there's some memory profiling done to determine the number of available memory blocks per worker. So instead of kind of naively trying to do something, we actually, wind up knowing exactly how much memory we have for each worker. And what that means is that it's, we're able to very, very confidently manage our memory, and we're able to understand where specific pieces of information live in our memory. And that helps a tremendous amount. Knowing where something is in memory, being able to manage it very quickly is part of what makes this so good. And this is from the research from the VLLM team, where they made the determination that for a lot of cases, the actual inference is memory bound, which means that we're limited by how much memory we can move in and out or move around. Now, once we have these blocks, we pre-allocate some KV blocks using their cache manager, which is from the PagedAttention paper. So what that means is beyond just the KV cache being great, which Greg talked about, we use a very specific managed KV cache, which is going to help us to squeak out even more performance, right? So the idea is vLLM behind the scenes is really just doing a number of very specific and important memory management techniques, which is huge, right? So, the idea is if you know where things are, if you're not taking up too much space, you're able to do this very, very swiftly and cleanly with vLLM, and that's what makes it so amazing. Beyond just an effective management of memory and making sure that we're using our memory as optimal as possible through the PagedAttention mechanism, we actually also have a really robust scheduler. And our scheduler is going to be what kind of coordinates our workers and ensures that we have the correct attention paid to certain jobs, that we're able to squeeze jobs in where they fit, that we're able to swap, destroy, recreate blocks of memory. And we're doing this all, as quickly and optimally as we can. So, behind the scenes, it's just a ton of GPU memory management that lets VLM be so fast, right? Where we're really carefully considering every part of our inference routine, and we're optimizing it as much as humanly possible. At the end of the day, though, the workers are what do the work. It makes sense, right? And they are the entities that actually wind up running the PagedAttention, as well as the other parallelized tensor parallel layers. But that's it, right? So in essence, VLLM under the hood, when in the server configuration, has a scheduler. The scheduler is the thing that's going to assign jobs, move tasks, ensure that they're in the correct place. Our workers are going to be what choose through those tasks. Our KV cache is going to be a managed cache that is in part pre-populated, right? So there's some pre-processing that happens here. And this is all done in a memory-aware setting. So we're able to really squeeze all of the memory orange to get the best, inference juice, or however you want to say that. But the idea is that because of all of those things that we just talked about, we can do cool stuff like send a request, like, how cool is vLLM, and generate 100 tokens in this amount of time, right? Which is incredible. It truly, if you're going to use these models in a production environment, and you're using a compatible model, basically you should just choose vLLM. It is a fantastic service. And with that, I will kick you back to Greg so we can hear close out before we do some Q&A.
Yeah, thanks, Chris. Getting that juice, that serving juice out of it, man. That was awesome. I think overall today we did see that this is super easy to use. The kind of at the core of what's happening here is this caching of the K&V. So just to sort of really super laser focus in on this as we wrap, caching of K&V by itself naively, not bad, and wasn't really happening necessarily everywhere you looked, but it's pretty good already. Next level is doing it intelligently, and that's where PagedAttention comes in. So, more and more of this stuff we're going to continue to see as, architectures stand the test of time. Really how to optimize and deal with them is going to be something that continues to be a huge area for research, for development, and hopefully for startups too. So watch the vLLM guys for sure. We saw some analogies for the QKV. We saw a RAG analogy where Q is the query, K is sort of all of the docs you might want to find similarity to, and then V is kind of scored docs. Keeping all of the scored docs in memory probably makes more sense than rescoring all the docs all the time. The restaurant analogy is sort of the custom request, the menu in the server's mind, and then the value is sort of the plating of the food, which is also represented by the menu. And we saw that attention has got that new token where K and V are sort of the same. They are all other tokens. Now, again, none of these are perfect analogies. And when you actually look at the computation of attention on sort of a really complex real problem, again, we're not using word level tokens. There's a little bit of dimensionality associated with batching we need to talk about. We are going to hold a YouTube live event on attention specifically next Wednesday. Watch that announcement coming soon. But for today, that's a wrap, and we're going to go ahead and start taking questions on Slido. Chris, let's come on back up and start tackling these bad boys. So first one up, is the server part only the FastAPI part while the rest of the improvements are in the inference? For example, the schedulers, workers, PagedAttention, etc.
So it becomes a little bit tricky, but no, the scheduler I would consider as part of the serving side or the service side, right? So while it is directly relating to inference, it's scheduling jobs, it's more akin to a server function, right? The idea is that we are using the scheduler to determine which jobs to do and in which order and by which availability. So it is, it's more about choosing which inference piece we're going to do. And so I would put it more towards the server side. Though it's not unique to vLLM. The way that they're using it is tightly integrated to their library.
Okay. So I like this one. Are closed source systems like ChatGPT probably built using similar vLLM-like approaches for inference and serving, since it's like so fast and it's obvious like how to use it?
I mean, I can't really discuss because I don't know for sure. But what I would say is that if they're not using inference optimization techniques, they're wasting a lot of money. So I would have to assume they're doing something like vLLM. Again, can't speak to exactly what. There are also a number of different inference optimization platforms. You have, we have one from, I think, Titan ML. There's NVIDIA has an inference optimization platform. There's lots of different approaches to this. So to say they're probably using something that does something similar to this, it must be true. But how similar it is to vLLM, you'd have to get them to reveal their secrets. So.
Yeah. Well, and just to kind of connect this back to last week for those that are following the series of the past few weeks, like aren't the sort of AWQ and GPTQ quantization papers, techniques, aren't those associated with inference optimization more than with fine tuning? Is that correct?
Oh, yeah, for sure. So AWQ and those aren't useful for fine tuning, but they are very useful for inference.
Yeah.
They provide a lot of power, both by making inference faster, so flowing information through the network, but also, and probably most importantly, reducing the memory footprint of the actual models. Yeah.
Okay. Yeah. So shout us out in the chat if you want to see a sort of AWQ GPTQ event. It's something that we're thinking about. So next up, are the graphs optimized with the caching? The neural network layers have the caching implemented?
So yes. So I think they're touching two discrete pieces of the network, and they don't have to be different. Cache is just a result, right? So we are going to compute information that we potentially can compute by flowing through a graph, and then we hold the completed computation for use later. So I wouldn't say those are distinct things. And so yes, I think the answer to your question is just yes. We flow through an optimized process, and then we cache that result. So we're getting optimization when we first compute, as well as optimization after we compute.
Okay, and then we'll wrap up with this one. Like, what are the pros and cons of using like Hugging Face transformers versus Hugging Face TGI versus vLLM for inference? Like, why would you pick one over the other? Or would you just always pick vLLM? Is that sort of like the go-to now?
I would definitely stay TGI if you're in the Hugging Face ecosystem already, or you're using their custom containers for hosting. If you're already, TGI is great. It is definitely not bad. It's unfortunately, TGI is now no longer truly open source, right? It's kind of open source, and using it for industry applications is not possible at this time. With the newest features that they've released due to some licensing changes from Hugging Face, boo. But it's still great. And if you're using it with their ecosystem, it's going to be great. For all other cases, definitely vLLM when it's compatible. It is an additional engineering lift to make it compatible if it's not already. So that's going to take engineering hours from your team. But if it is, I mean, heck yeah, just use vLLM. It will be better than just the Transformers pipeline. Transformers pipeline is super useful when you're iterating and you're not yet worried about, latency. So we're just doing experimentation. We need something to go quickly. We don't really care. Hugging Face Transformers pipeline is going to be great for those things when you're still fiddling and everything like that. But once you get users using your model, please swap to vLLM, save yourself a couple bucks. And save your users, a few milliseconds or even more of inference latency.
Nice. Yeah, and on this last note, I think everybody just watch out for these vLLM guys. They did their first sort of in-person meetup. We dropped the slides in the chat here. One of the last things we dropped, and they're talking about their roadmap. They're talking about the things they're going to build next. It seems like they're on a great trajectory. I mean, they were funded on an open source grant from A16Z, so don't be surprised if you see these guys raise some money soon and become like a full-fledged startup and start crushing in the space. So definitely thanks to everybody that's asked me for this. Thanks to everybody that joined us today. Chris, thanks for answering questions. We're going to go ahead and wrap. We've got one announcement to make today that I'm pretty excited about. So if you like our stuff, one of the things that we did is we recently released a brand new course, and this one sort of subsumes all of the other courses that we've had. So this one is brand new for 2024. It's called the AI Engineering Bootcamp, and we are going to use it to cover everything. This is going to be our flagship course from now on. RAG, fine-tuning, agents, eval, visibility, serving, great projects, prototyping, and production. We're going to split it up. And this is going to be now a 7-week boot camp that is going to be truly end-to-end. So if you're trying to become an AI engineer, check this out. If you have questions, feel free to reach out to me directly. But very excited. Check this out. Would love to get your feedback on it. This is everything that we've learned from running LLM Ops and LLM Engineering, all combined into one thing. So check that out if you're into it. Otherwise, See you next week for the attention. We're going to go even deeper on attention next week. And for today, if you have any feedback, please do share that with us. We've got a feedback form that we'll throw your way. And that's it. Until next time, you know what to do. Keep building, shipping, and sharing, everybody. See you soon.